Hello everyone, I'm Laurence from XP. Thank you for coming to this talk. Thank you for the organisers for inviting me. Before I start, I'll probably just explain my t-shirt because people do ask. This is my emergency maths t-shirt. In case of emergency and I need some maths, I can just look down and read the equations. I have them there. Okay, but today I'm going to be talking about zkML. And what is this? Two different areas, ZK and machine learning. You could just see this, maybe you're thinking this is just going to be a combination of two buzzwords. Well, that's not the case. It is a useful field in its own right, and it's the combination of zero-knowledge proofs and machine learning. Why we want to do this is that if we have some machine learning, we want to be able to prove that this has been calculated correctly. But we want to be able to do that with zero knowledge, which means we have privacy added to the process as well. Some of the terms you need to know, inference. In machine learning, inference is where we run the forwards through a model. So this is the thing you do every day. When you use a large language model, you put in a prompt and it does the inference stage and it comes out with some output. We want to be able to show that that was done correctly. Would be nice if we could have private inputs. So when you're using ChatGPT, etc., they're not private inputs. They're being sent off. They're public. But with zkML, it makes it possible for people to do private computation and have it checked and proven to be correct. And then, of course, we know that ZK has been used very successfully on chain as well. We can create proofs of chain and then put a proof of the computation on chain. That's the basis of a lot of the roll-up technology. Okay, so I'm doing this assuming you have no experience of ZK or ML. Just going to talk quickly about ZK. I'm sorry this is not very big, but I think you've got some screens there. So in ZK, what we do, we have some kind of computation we want to do, and we turn this into what is called a circuit. And this can then get compiled into some type of representation, and there is a kind of a setup that goes on. This results in two summaries of the setup, a proving key and a verification key. And that is then, once we've done that setup, we have everything we need to then start to create proofs. So when we want to create a proof, we can put in the inputs to the proof. This is called the witness generation. The inputs then go to a prover, and there may be some public inputs as well. You don't have to only have private inputs. But then the prover can create a proof of the computation, can send that to a verifier. The verifier uses their summary of the setup, which is called the verification key, and they can easily verify that that computation was done correctly. And one important aspect of this is that it has to be what is called succinct. When the verifier is proving that the computation was done correctly, he could, of course, just run the computation himself. But we don't want that because that could potentially take a long time. So that is the point of the succinctness of the proof. He could prove something, say, in milliseconds, that is a computation that would take any amount of time to actually compute. Machine learning. So in machine learning, there are different ways to do it, but one of the very popular approaches is using neural networks. These are based on something called an artificial neuron. What we have with those is a number of inputs coming into the neuron, and these are adjusted according to weights. Okay, those are then added together. We then pass it through something called a threshold function, which decides what the neuron is going to do. Is it going to give an output depending on the inputs it's received? And then that output will go to another neuron. And, okay, I don't have a slide to show that. We don't do these sort of, individually. We don't just have one neuron. We have these in layers, and we have many, many layers. And the models, the large language models, etc., will be hundreds and hundreds of layers deep. And this is called deep learning. So the thing you need to remember about this, we have lots of neurons, but also we have lots of weights as well. There are also other things called biases, but I haven't got these in the diagram. But what I want to get across is that that there's a lot of configuration that goes into this. So this is the inference stage. This is when the model we're using has been trained. So when you're using a large language model, this is what is happening. You're putting your inputs in, your prompt, it goes through all of these neurons, and it gives you an output. It generates some text. But before it can do that, it needs to be trained. And the training consists of setting up these weights. We start off effectively with a kind of a blank model, and we do the training aspect, which takes that model and then configures it so that it can do something useful. That training aspect is very computationally expensive. And what I'm going to be talking about mostly in zkML is proving that the inference stage is working correctly. It's less computationally intensive. So what will we do? How will we use zkML? What's the typical use case for this? Well, imagine that you want to use some machine learning. You've got some input. You want to have something done with that input. And it could be, it could be like a large language model, some text, but it could be something more specific. It could be perhaps something that has some privacy involved. Maybe you've got some medical data and you want to send it off to be analyzed by some machine learning model. So you may want your input to that model to be private. You don't want to share that medical data. So what will happen is you will send that off to some provider, somebody who's going to do the inference stage for you, run your input through a model. That will depend upon your input X and then the weights. The model has these weights, this configuration of the model. This produces some output, O, and also a proof. So we're producing the output that you want. The medical data has been analyzed and it says, yes, this shows that this particular thing is okay. But also it creates a proof to say, not only do you have the output, but we have a proof that that was calculated correctly, and we have a proof that it was done on a particular model. And so your machine learning consumer then gets back both pieces. So it gets back the output it wants, but also the proof that everything worked correctly. And proof that a particular model was used. You could have sent off your input to some provider thinking they're going to use their most expensive up-to-date model, only for them to use something else. So this is why you would like a proof. Okay, so yeah, that's the first one use case I've just shown, that the sort of idea of privacy. Other things, media authenticity. So recently, since large language models, etc., came out, we have the ability to create fakes. We have the ability to create fake images. We can certainly generate text easily. We can generate audio, fake audio as well. So what is useful about zkML is that we can then use that to try to prove the origin of media. So this has been done, for example, with a microphone, where the microphone takes an input. It will then create a proof of what that input is, and then what it allows you to do is to transform that input. So similarly with what's just happened here, with this microphone, my voice sounded in one way, now it sounds different. There's kind of a transformation of the sound. We can do that with zkML. We could take that original audio, transform it, say, to remove background noise, and then we can prove that that transformation is all that was done. We didn't actually change the original input so that the person appears to be saying something else. We just filtered out some noise. Okay. The next point here, this EIP. This is for people who want to generate images, for example, for NFTs. And it's a way to then prove that the prompt they sent in to generate the image was actually the correct one, that was actually used, and the way that the image generated was done correctly. So therefore, when you get the NFT, you also get a proof that that was generated in the correct way. Other possibilities in games, if we have agents playing games, but they're using some type of machine learning for intelligence, we could have some proof that that was done correctly. So maybe you're playing against some character in a game, and it's claimed that they have a certain ability. But of course, the designer of the game could cheat and make it give them more ability than they claim. Well, with zkML, we could prove what model was used and prove that the inputs to that model were correct, that maybe they didn't have extra information about the game. Identity and biometrics, I don't think they've been here, but there's a company called WorldCoin or World ID, or I think just World now, who give you an identity on chain. And what they do, they have special hardware that will scan your retina and it will produce an identity for you. But of course, if you're going to do this, you'll be worried about that biometric information being leaked. So what they say is that that information will be computed into this identity. A proof is created to show that's done correctly, but that proof is all that is needed. The actual original biometric information can then be discarded. Now, I've already spoken about the medical data. Why would we want privacy? Well, yeah, we may have important business information involved in some input, so that we don't want to leak. Also, the model itself. When somebody trains a large language model, there's a lot that takes a lot of time, there's a lot of cost. That configuration is very valuable. So maybe you don't want that information to become public. So again, zkML can be used in that sense. It can be used to show that some inference was done, but without giving away details of the configuration of the model. Okay. So the question, could we do everything privately? Well, of course we could. We could run our model privately. We could do all the calculations privately, but there are disadvantages to that. First of all, there's the cost. It may be very difficult for people to use very large models to train them, etc. But also, I mean, we may want to be able to learn from other models. And this, for example, there's a field called federated machine learning, which allows models to share or to learn from each other and to do their training collaboratively, but without giving away private data. Okay, there's World ID. That's what I was saying about getting your retina scanned. That's the hardware they use. It's called the orb. This one, this is an example. This is for verifying that nuclear weapons have been decommissioned. So this slide I got from Los Alamos Laboratories. What it is useful for showing, and I don't know why Darth Vader is there, what's useful for showing is that they're using a number of different techniques to show that the final result is correct. So they've got information coming in, they've got video information coming in, they've got a neural network running, so they want to be able to prove that that was working correctly. They want a signature being involved. So all of this needs to be combined to create a proof that can be given to someone to verify, but without giving away secret information and sensitive military information. Okay, I'm going to skip through this, I think. So this all sounds great. And zero-knowledge proofs, they prove computation in a general sense. And so machine learning is just computation. So it should be a piece of cake then, just to combine the two. Shouldn't it? We should just be able to prove computation of machine learning as we can prove any other computation. Unfortunately not. And there's a fundamental problem, a fundamental disconnect between the two areas of technology. And this is down to the types of maths that is being used, the underlying maths between these technologies. So in machine learning, these weights that I mentioned, these are floating point numbers, and we do lots of calculations. We use matrices, and we are multiplying and adding these things together. Lots of floating point calculations. Zero-knowledge proofs at the moment rely on integers only. So they're built upon finite fields of integers, and these so these two technologies don't easily fit together. The underlying mathematics for the two doesn't fit together easily because we have these different types of numbers that are being used. So zk is difficult for that to use floating points. And then for machine learning, they want to use floating points because you get lots of precision. You don't want to just have integers involved. The way that zk works is that we start with some program, or maybe that's some model, and we convert it into what is called a circuit. Okay, that is difficult to do with the types of machine learning models that we have. Also, there's just the general area that both of these areas are fairly complex, and so it's difficult to combine the two areas easily. There's not a lot of experience across these two areas. And then a final point is about determinism. So zero-knowledge proofs need determinism. They need to know that if you put in a certain input to some computation, that is always going to produce the same output. With machine learning, although you can have that, they can be completely deterministic, what you often get is that randomness is added. And this helps with things like generation of text and generation of images. And you will see this if you want to have an image, if you put in the same prompt to an image generator, it will produce different images over time. They're slightly different, but they are different. And the zk aspect wouldn't like that. It would see this as being, it would see that as being false. The proofs wouldn't match because we have different computation going on each time. So that's another problem. So you can see there are quite a few difficulties we have trying to get these two things together. So if we wanted to do this, though, if we wanted to model a neural network, if we wanted to make that so that it's usable in zk, can we do that? Well, even though they do actually look similar, so the architecture of a neural network and the arithmetic circuits that we have in zero-knowledge do look similar. They're difficult to map directly. If we took a very naive approach, what we would find is that the time taken to do anything on the zk side would just be prohibitive. So we have to sort of think of some clever tricks to do that. But there are companies around that have managed to do some of this and get some success. So there's one library called zkML, rather confusingly, but that's from Daniel Kang, and he's done things around things like media authenticity. One of the most used libraries is zkL, and this allows you to develop a machine learning model, and you can do this using the traditional machine learning tools, such as TensorFlow or PyTorch, whatever. And then you turn that into a standard format, what is called an ONNX format. And then zkL can take that and create a proof from that. And I don't know how many people here are developers and want to develop on this, but my advice at the moment, I think, would be if you want to do something relatively easy and want to use something that works and has been around for a while, zkL is quite a good choice there. RISC-0 is a slightly different approach because this is a way of doing computation and then proving it. And it allows any kind of computation, which means that you can also do machine learning with that, and people have done this. But again, you really do need optimization when you're trying to do zkML, so it doesn't naturally fit together very well. If people are aware of the Mina blockchain, they have their own version, their own library called Mina zkML, which takes an approach which I think could be promising. So Mina is all about recursion in proofs. You can take a proof and then take a proof that proof was correct, and so on. You can recurse through proofs. So what this could offer us is when we have a neural network that is built of many layers, we could recurse through these layers. So you're splitting the problem of the computation into smaller pieces and then producing smaller proofs, which can then build up into an overall proof. the final one here, so SumCheck and GKR, these are aspects of, or ways and techniques of producing zero-knowledge proofs. And they were kind of overtaken. They've been around for around 20 years. They were kind of overtaken by other techniques, but then more recently they've been picked up again because they do work quite well with machine learning. And Modulus Labs is a company that has used these quite successfully. So there, yeah, that's Ezekiel. I'll go to that. I think I've explained all of that. The basic point about this, without going into the details, is that, excuse me, when we're doing this, we do need to use special techniques and special workarounds to try to get it to work efficiently. Now, the thing here, quantization, this is an idea that you can use with machine learning. So in machine learning, we've got these weights. We're going to be doing computations. We're going to be adding these weights together, multiplying them by the input, etc. And that is problematic for zk. So one thing you can do is you can turn these weights, these floating point numbers, into integers. You can just multiply them up until you get an integer. Obviously, you have to remember how much you multiplied them by, but that is possible. You can get an integer representation. That will work. The problem it gives, though, is that we need to do this, at all stages of the computation. So it adds an extra overhead. But that is a technique that people have used. The other idea as well is to reduce the precision. So if we have a 64-bit floating point number that we're going to use as a weight, for example, we could try reducing the precision and representing it as a 32-bit. And this does work. You can reduce the precision down and down, and machine learning will still work, but it will degrade as you reduce the precision. The accuracy and the sophistication of what the model produces will reduce. So you can only go so far with that approach. The other thing that Ezekiel does is to use these things called lookup tables. So this again is a technique that is used in zero-knowledge proofs, where in zero-knowledge certain computations are expensive, and you could do these in a very standard way, but a cheaper way to do them is to use things called lookup tables, where we put all possible outputs into a table. And then rather than calculating, so this is done ahead of time, rather than calculating the result, we just provide a result and then say, well, is this in the table? And if it's in the table, then we can say, well, that proves that this is correct to some extent. So this is a general technique in zk that has worked well, and Ezekiel also used this. Yeah, so this shows the approach that Mina have taken. Really, this is just repeating what we do in a neural network. We have matrix multiplications. A ReLU is an activation function. This is very just standard machine learning operations. But you can see here they add extra things to this, such as doing range checks. They're checking that the outputs are within a particular range, which you can then have as part of your proof. As I said, GKR has proved to be quite successful. This is because the way that it works does model a neural network quite well, and it's quite easily to take something like a neural network, which has many layers, and we're summing from one layer to the next, and we can quite easily use that with the GKR style of zk to create a proof. It fits much more easily than some more recent zk approaches. And the basis of this is something called the SumCheck protocol, which is just a cryptographic technique that is found to be useful. So I said Modulus Labs have used this. This came from an image about 18 months ago now, I think. So far I've been saying, zkML is hard. We can't prove things very easily. Everything is too expensive to do with zk. So that's kind of the top image here. But then what they did is they took ChatGPT-2. Now, okay, you know, we're a few versions ahead of that now, but that version of a large language model, that had just over 1 billion parameters, and that was seen as really something to aim for. If you could get over 1 billion parameters and produce a proof of that, that would be quite an achievement. And that's what they managed to do. So they took a prompt, put it through ChatGPT-2, and got the output, and then they also created a proof that that had been done correctly. Now, that sounds great, and it is good. It was a milestone, and you know, it's useful that that's happened. The small print, though, is that the setup for the zk side took 90 hours to do, and the proof also took 90 hours to do. So it's not the kind of thing we can easily use if we want to prove, you know, we've done a prompt and it came out correctly. You wouldn't want to wait 90 hours for the proof that was correct. But still, we've passed a milestone here. We got over 1 billion parameters. Of course, the latest large language models are, you know, hundreds of billions, trillions of parameters, but we are moving in the right direction. So other techniques, so there's a project called zkLLM, so zk large language model. Again, they're taking the approach of we need to do special techniques. We can't do vanilla zk, we have to do special things and tweak the way that we do things. And so they use lookup arguments, lookup tables as well. They also have specialized activation functions. So those functions I spoke about in the neuron that decide what output is going to come out, they've written special versions of those that will work better in zk. zk attention as well. This is because the large language models are based on what's called the transformer architecture, which is it's based on an idea around attention, that it is able to attend to a large amount of data. And so for large language models, we also need something to help with that side as well. So that's what zk attention does. So I've spoken. Oh, I should also mention there's a more recent company as well called Lagrange that have made advances in this area. Fortunately, it happened too late for my slides. But they have done something called deep proving, which again they've managed to tweak the way that they can create the proofs, and then but rather than just calculate the proof on a single machine, they have a network, so they can parallelize the process and put out the proof or the demand for a proof to a network and get it done in parallel, and then combine it back into a single proof. So that's another company worth taking a look at. So, but other things we can do if we want privacy with machine learning. As I said earlier, you could do everything off-chain. Certainly that is possible, but then you know, you can do it privately, but then you may want to interact with other models and interact with other systems. Mina does help with this a little bit because the basis of the Mina blockchain is that it allows off-chain computation. So in Mina, you do some off-chain computation. You can do private inputs with that. That will change some variables, some state, which is then uploaded on-chain, and you send a proof on-chain that was done correctly. But there is privacy involved. Because we have a zero-knowledge proof, we don't upload the inputs to our computation. So that's one possibility. Recursion, as I was saying, I think this is a promising area also. We could potentially recurse through layers of a neural network. We're splitting the problem down into smaller parts, and then we can create proofs more easily. The third point here is something that came out of a hackathon a couple of years ago, a zk hackathon, and it really goes to the fundamental way that machine learning works. So what I've talked about so far, I've been mentioning these neural networks and that they have weights. These weights are floating point numbers. That's really a big problem for us. So they looked back, the people who set up the weightless network, which is called zero gravity. They went back and said, do we need weights in neural networks? Are there other approaches we could take? And they've managed to find one. And so what they've done is to create neural networks without weights, which are then much easier to integrate on the ZK side. The next point here is, because at the beginning I said ZK works with integers, but recently people from Nethermind have done research and started to find techniques where they can do ZK over rational fields. So rational fields means it's not just integers, we can also use fractions as well. So we're moving away from this big restriction of numbers that we have in ordinary ZK to the more open types of numbers that we could have in machine learning. And then other approaches that have been taken, so there's OPML. So if you're familiar with roll-up technology, you'll know that there's basically two approaches. There's optimistic rollups and there's ZK rollups. So there's a similar thing with proving machine learning. So there's a company called Aura that do OPML, where you create you do your computation, you do your inference, and you assume you take an optimistic approach that it's correct. But then you have a means of challenging that. And in order to do that, you need economic incentives, so that has to be done on-chain. And then the final thing I have there, FedML, this is federated machine learning. This is something that's been around for quite a long time and is nothing to do with blockchain particularly, but it's an approach that allows people to share training of models. So if you have, say, a business, say a number of automotive companies, they want to sort of collaborate on producing some model that's going to be used in vehicles, but each of them will have their data, but it could be private data. They don't want to share this business data with their competitors. Federated machine learning allows you to collaboratively train the models, but without giving away the details of the data to the other people who are collaborating with. Yeah, there you go. There's zero gravity. That's the one with the weightless models. That's about zinc. So this is where Nethermind produced the rational fields. That's about Aura, OPML. And that's a company that does federated machine learning called Flower. Okay. So yeah, this, as I said, I'm just repeating myself here. These are some of the limitations. The inference, even with the best models, the inference proof times can still be seconds to minutes. When we take the ZK aspect of this computation of the machine learning, it can produce very large circuits, which affects performance. So we tend to have a trade-off of accuracy versus performance of the machine learning model if we want to try to get it small enough to use in ZK. But yeah, this is an active research area. People are working on this very actively. There's some benchmarks. This is, well, linear regression, so very simple. Nothing like a large language model, nothing of that complexity. But it gives you an idea of some of the numbers. I'm just comparing Ezekiel here to RISC-0. So Ezekiel, proving time of 1/10 of a second, that seems reasonable. But that is, linear regression model is very simple in AI terms. But there you go. There's from zkLLM, we have 13 billion parameters, and that took 15 minutes to prove. So we are progressing quite a lot. So that's it. If you're interested, where can you go from here? Well, there are lots of resources. So DC Builder, he works with World. You may well see him at conferences, but he has a great number of resources. And they do a very good introduction to zkML as well, so I've given you a link to that, and an awesome repo from them. If you're interested in ZK and well also Web3, the Zero Knowledge podcast is something I can definitely recommend. They get the top people, the people who are actually building, the latest things, doing the latest research onto their podcast, and they produce podcasts that are quite amenable, quite easy to understand. So I would recommend you check out that podcast, and they have lots of episodes about zkML as well. There's a paper there about using zk snarks with looking how they can change images and how that can be done in a way that can be proved to have been done in a particular way. Okay. Yeah, that's everything from me. I'm happy to take questions. If you want these notes, they're on our website. We also have courses about ZK and Web3, which is on at our Academy website, so please check that out also. But yeah, if you have questions, I'm happy to answer them now. Go ahead, yeah. I'm Yeah, this is a problem. That was the deterministic problem that I spoke about. The fact that they tend to use randomness when they're doing generation. You can take that out of models, so you can take out any idea of randomness, but that tends to be added in to improve the quality of the output. So for zkML, what they do is tend to try to take that out to so that they can create a proof. Well, I mean, it is possible to take out the randomness. You don't have to have randomness in machine learning. You can make it deterministic. The other thing you could do is on the ZK side is to do things like range proofs to prove that maybe the answer was within a particular range. But yeah, I think, for example, with the ZK LLM activation functions, I think they tweak those to work in a particular way that can be proved that maybe the answer could be different each time, but it can still be proved to have been calculated correctly. So, for example, with a classification task on a neural network, you will have an output that is a series of probabilities. It will come out with, 10% probable of this, 20% probable of that, 50% probable of the other. So your machine learning model is going to pick the highest one, but you could still prove that those probabilities were worked out correctly. So I think there are workarounds, but it is a valid problem with ZK. Yeah. Thank you. Okay. If there are no more questions, thank you very much for your attention today. Thank you.